For an example for ANOVA, and again, ANOVA stands for Analysis of Variance. The idea here is the chi-squared goodness of fit test is an extension of two proportions being compared, and ANOVA is an extension of two means being compared. We can even see already in the beginning of the hypotheses here, this is about comparing multiple means to each other. We'll go through and select the correct answer here. But if we had 3, 4, 5, 10 means we wanted to compare to each other, we can't quite do that with the previous chapters we've done where we were able to compare two means to each other. So this is an extension of that. In the background though, this works quite differently. This has a different distribution to calculate its p-value. So this relies on what's called the F distribution. And that actually has a built-in, or that's constructed as a fraction. And so the numerator and denominator of that fraction are each part of the problem. So we're going to be doing this quite a bit different than most of the other hypothesis tests. We're going to use the Analysis Toolpack, so you do have to have that installed, or you can maybe find an online calculator to input that instead. So calculating the information ourselves would be a little bit too much work here. So we're going to focus on the hypotheses, not focus too much on the calculation, and then get to the p-value. So the hypotheses for all ANOVA, and this does not change. All that's going to change is how many different means you have. So the null hypothesis is all of the means you have are equal. So that'll normally be written as however many different means you have will all be equal to each other. So answer choice A here is a correct null hypothesis. Answer choice B looks like a correct null hypothesis. The alternative hypothesis is that one of those means is different, and we don't know which one it is, and it's at least one because they may all be different, or some set of them may be different than the rest. So ANOVA does not quite tell us which means are different, and this is more of a preliminary test. So we have data that we're going to compare multiple means to each other. So for this example, we're comparing vacuum cleaners and the weights of different vacuum cleaners based on are they at upright or are they a top canister? Not quite sure what all those mean. Let's see. Bagged upright, bagless upright, top canister. So, but essentially different types of vacuums. So the BU must stand for bagged upright. BLU must stand then for bagless upright and top canister. So those are the three categories we are comparing. The alternative has to be essentially in words. It's very difficult to write this in some sort of symbols. At least one of the means is different than the others. So all of the means being equal is always our null hypothesis. An alternative is almost always in words. It's much easier to describe this in words. At least one of the means is different. So I'm going to copy my data over. We can copy instead of opening it in Excel. So we don't have to open a new sheet every time. But I am not going to do much of the calculations myself. So after installing the Toolpack, it'll be in the Data tab, and we will choose ANOVA single factor. So ANOVA, I think the textbook is going to refer to that as one-way ANOVA. Two-way ANOVA would just allow us to compare two variables. So our input range here. I didn't select the labels, so I'm not going to choose labels. And my data is organized by columns. Each of these columns is different, so just make sure to be careful with that. I like to output my range on the same page I'm working on instead of a new page. Okay, and so that's it. So this is going to get us all the information we need. One of the conditions for ANOVA is that all of the variances look equal, and these are not particularly equal, but they may be close enough to continue. In terms of going through an example homework problem, we aren't going to be asked to check the conditions, but that is the main condition we would need to check. And so here would be the calculations that we are not going to worry about doing right now. And this between versus within is how ANOVA is calculated. And essentially one of these calculations becomes the denominator and one of them becomes the numerator of this F test statistic. So this is the test statistic that we're looking for. So we'll highlight that. And this is the p-value that we are looking for. If we tell the Toolpack in the beginning the correct alpha value, it will actually get us the critical value that we need. So I'm not sure if I gave it the right one. If we need to fix that, we can change that. So what's compared here is the means of each sample and then how the standard deviation or variance in the sample looks. So if the means are very different and the standard deviations are very small, we would be confident that they would be different. All of the values for one of them might be clustered around, so let's see if we can look at that. So one of the means is 21.5, one of them is 21.3, and one of them is 24.3. So it looks like the third one, top canister, might have a much larger mean. If this standard deviation or variance is small, then we can be confident that it's different than the rest, and so that'll show up in a large F statistic. So this is always a right-tailed test, but I'd like you to focus more on the p-value. So we are asking something to calculate this for us. We might need the F statistic itself, but we can focus on interpreting from the p-value here. So we go ahead and input this, round to 2 decimal places for our F statistic. And our p-value. So round to 3 decimal places here will be 0.048. So, we didn't do much setup on our own, and we're already done and going to be comparing our answer. There are other calculators out there if you're using Google Sheets. So our null hypothesis is that all the means are equal, and our alternative hypothesis is that at least one mean is different. And so this is like a combined step 2 and 3. Our test statistic and p-value are being done for us with software. What does that mean when we make a decision of? This p-value is a little bit or somewhat less than alpha at 10%. Our p-value is about 4.8%. So we are going to reject the null hypothesis. So we are assuming now that at least one mean is different. So at least one mean, which right now is a weight of the vacuums, is different. And it doesn't tell us if they are all different, and it doesn't tell us which one is different. With a kind of quick look at it, it does look like the third group of the top canister vacuums is larger, but unfortunately we cannot get that information purely from an ANOVA. So lastly, it doesn't appear there's a direct claim here. We are just asked to test. So let's see how the wording is answered. So we are rejecting, and let's look at these two. Since we rejected, we get to use the phrasing that's a stronger wording here, that there is enough evidence. There is enough evidence to conclude that the mean weights vary. So what that is a rewording of the alternative hypothesis. So if we reject, that means that we are essentially crossing out the null hypothesis and taking the alternative hypothesis to be the correct answer. If we fail to reject, nothing is quite sure because there was an initial assumption of the null. So there is no particular claim, but if we are accepting the alternative hypothesis since we rejected the null, we can just go with that and assume from there. So at least one mean is different. So there is enough evidence. This is because we rejected. We can make a strong answer here that at least one mean is different. And you can see I already worded that earlier. So this isn't quite a comment on the claim. There is no claim. It's just an interpretation of what does it mean if we reject the null hypothesis. Okay, looks good. We notice that they will not ask us to determine which mean is different. That would require further tests or some sort of further analysis.